In this lesson, we're going to look at a person climbing a rope. The reason I have dedicated a full page of notes to this is that the language it's a little tricky, and the application of the forces in the problem is a little tricky. So I wanted to make sure we had a full discussion on this, and then we can also talk about it together in class. So in this problem, you're told that you have a 75 kilogram person. So that's the mass, right? Kilograms is mass. So we know, again, I cut to the chase. MJ, get the weight of the person trying to climb the rope, if it's a 75 kilogram person, is a 735 Newton person. And what I have shown here is the situation where the person climbing the rope has not yet started to move in terms of how we should be thinking of the problem. They just jump up, grab the rope, and they're holding themselves in place. And when they hold themselves in place, we have to look at the interaction between their hands and the rope. So what is allowing the person to jump up, grab the rope, and not slide down? Well, the friction between their hands and the rope is what allows the person not to slide down. If we greased the rope up, or there was no friction between their hands and the rope, it would be impossible for the person to stay on the rope. They would just slide down. Well, how much friction does there need to be? Well, a lot. The frictional force in this case has to be equal to your weight force, your 735 newtons, just to keep the person from falling down. That's not going to be what it is to actually accelerate up the rope at 5 meters per second and climb the rope. So now you know why rock climbers, have extremely calloused hands. They're essentially supporting their whole body weight on the friction between their hands and the rocks, or in this case, the rope. Okay, so that means let's do the ons and bys and make sure we keep everything neatly understood. So the frictional force on the rope climber's hands is the force on you, if you're the rope climber. So the force on you by the rope. Well, that means there has to be a force on the rope by you. That will also be frictional, but that translates into the tension in the rope. And this is the part that I didn't think would be 100% intuitive to people. I think when you think about it, it makes sense. So that's why in textbooks and solutions, they're going to tell you the tension is pulling you up the rope. Actually, the tension in the rope corresponds to the friction, numerically, to the friction which is pulling you up the rope. But technically, it's friction. So when you see solutions in our textbook where they say the tension is responsible for pulling the person up, it's not quite 100% correct. Well, let's take a look at the rope itself. Well, the tension in the rope is now your body weight. And if the rope is going to stay attached to the ceiling, then there better be a force by the ceiling on the rope, or force on the rope by the ceiling or the hook, however you want to label it, keeping the rope from coming out of the ceiling. Well, to finish up this problem and see, well, how do we handle the person accelerating up the rope, we focus on just the person. So we have the friction in their hands, which translates to the tension in the rope going up, their mg going down, and that will equal the mass times the acceleration of the person. So the minimum tension you can have in the rope to climb a rope is your body weight. If we rearrange the equation as we did here to solve for the tension, notice we now get tension equals mg plus your mass times your acceleration. So if you're accelerating up up the rope, You'll have a positive A here, and notice the tension in the rope, let's factor the amount, will be G plus the acceleration that you have going up the rope. So that will correspond to the tension in the rope. Let's say as you're climbing the rope, you're getting nervous. You think that rope is going to break. You want to reduce the tension in the rope. Well, then you want to start going down, right? If the acceleration is negative, now the tension in the rope is less than your body weight. So if you're ever climbing a rope and it feels like it's about to break, you don't want to pull harder to try to get up faster. You actually want to let go a little bit and go down and have a negative acceleration. And if we take it to the extreme, if you totally let go of the rope, right? So if you totally let go of the rope, you are in free fall, and that would be minus G, right? So G minus G will give you 0, and there's no tension in the rope when you let go. So it's an interesting problem, and I don't think it's 100% intuitive relative to how the friction translates to the tension. So that is why I dedicated the page of notes. We have a couple of homework questions that relate to objects, climbing ropes. I think there's a monkey on a rope in one of the problems, but whatever. You have to be able to understand the analysis. So that is it for lesson 6, pulling on a rope.